So today we're going to see an RLC circuit in action. Here I have connected in series an inductor, this rather large coil right here, capacitor, actually it's 1, 2, 3, 4, 5, 6, 7, 8, 9 capacitors connected in parallel, and a resistor, and the resistor is this light bulb. And this whole thing is connected to a standard, it's plugged into the wall. When I close the switch, we'll see what happens in a second. When I close the switch, this R, C, and L in series are going to be connected to the wall, which means they're going to be driven by an AC voltage, which is oscillating back and forth 60 times a second. Okay, so let's get ready and let's see what happens. Here we go. I'm going to close the switch. Nothing happened. Let me try it again. Nope, nothing happened. Now, the neat thing with this setup is that I can change the capacitance and I can change the inductance. And I'm going to change the inductance of this inductor by sliding this, bar of iron, pulling it out of the coil. That's reducing the inductance of this inductor. And as I reduce the inductance of this inductor, let's see what happens. There we go. When I have the inductance of the inductor at exactly this value, the light bulb is burning very brightly. Now what happens if I reduce the inductance a little bit further? The light bulb dims again. If I increase the inductance a bit, I get to this special spot. The light bulb is burning very brightly. Increase the inductance further, and the light bulb goes out. So what's happening here is an example of a phenomenon that's generic throughout many, many, many areas of physics, and it's called resonance. So what am I doing when I'm changing L? Well, we know from our analysis of an LC circuit that there's a natural frequency in an LC circuit, and it's 1 over the square root of L times C. And so I'm not changing the capacitance here. C is, I haven't changed anything to do with the capacitance, but I'm changing L. As I change L, I'm changing 1 over square root of LC, and there's a magic value here when something happens. And what that magic value is it's the magic value of L, where 1 over root LC is 60 hertz. Because if I set things up so that the natural frequency of this oscillator, this LC oscillator, is the same as the 60 hertz, that's the drive that I get from my wall outlet, then what's happening as the wall outlet is pushing the current back and forth 60 times a second is the same as what happens if you push a child on the swing, if you push at exactly the right moment in each oscillation back and forth so that the child swings higher and higher and higher. If I push the child with the right frequency, the oscillations of the swing get larger and larger. If I drive this circuit at its natural frequency, the oscillations get larger and larger and larger, and you see a very large current. The light bulb glows brightly. Now, and what I'm doing when I slide this bar out is I'm changing the natural frequency, and this is the spot where the natural frequency is 60 hertz. And you hear this buzz, this hum. And that's also coming from the fact that the current is at its largest. When I have a very large oscillating current in the bulb, it makes the bulb glow brightly. And when I have a very large oscillating current in this coil here, the current is going back and forth, back and forth, back and forth in the coil. It's making a magnetic field going back and forth, and that's making various little bits of the support structure of this flex back and forth, all at 60 hertz. And what you're hearing, and I'll be quiet for a second, and what you're hearing is a 60 hertz hum. So how can we check that this explanation makes sense? Well, so what I'm going to do now is I'm going to change the amount of capacitance. So to do that, I'm first of all going to open the switch. And let me now reduce the capacitance. Okay, so if I reduce the capacitance, that means that in order to get LC back to where it was, if I reduce the capacitance, I'm going to have to increase the inductance to get the same value of LC that I had before. So this is about where I was, nothing. But now I increase the inductance, increase the inductance, increase the inductance, and look at that. There I get the light bulb glowing. So with less capacitance, I need more inductance to find that sweet spot, that resonant spot, where the natural frequency of my circuit is 60 hertz, the same as the driving frequency with which I'm tickling it. So the driving frequency is tickling it, is poking it 60 times a second, and because the natural frequency of the circuit is also 60 hertz, we get the circuit is in resonance with the driving frequency, and the light bulb glows brightly. And what you see is that resonance here is occurring with a larger value of the inductance than was the case back here. So now I just increased the capacitance again, at the risk of getting shocked, but don't worry, I didn't get shocked. Now, no resonance until I reduce L. So I increased C, so I have to reduce L, and I reduce L, and I get the light bulb glowing brightly again.